This is Unit 6.1, Interpreting Scatterplots. It's the first note in the Investigating Relationships unit. So the first thing is to just take a look at the graph that we have here and just answer these three questions. You're supposed to do this on your own, but I'll go through them now. The graph shows the plotted points rising upward to the right. Do you agree, do you disagree, or do you pass? And pass, just, you actually don't have the option to pass. So I agree that I see that for the most part, this set of data is rising to the right. 2, as the length of the tibia increases, the length of the leg increases. Yes, as I read the graph from left to right, the points are rising. So as tibia length is increasing, leg length is also increasing. So I agree with that. The graph can be used to estimate the length of a person's leg if you know the length of the tibia bone. And yes, I agree with that. Suppose I have a length of a tibia like right here. I can come up and it looks like it's going to be somewhere for the length of the leg, somewhere around here, whatever those numbers are. I don't know what they are and it doesn't really matter. But we certainly know that the leg length is not going to be way down here, and we know that it's not going to be way up here either. So we can estimate that it's going to be in this area. The graph shows, so for the second one, this is the number of baskets versus the distance from the basket. So the graph shows the plotted points falling to the right. Yes, as we move to the right, the points are coming down. So I agree with that. As the distance from the net increases, the number of baskets made decreases. Yes. So again, as the distance from the baskets increases, we are getting less, or we're making less baskets. So yes, that's true. And the graph can be used to estimate the number of baskets you will make if you know the distance from the basket. Yes, if this is the same person that's doing this, if they're standing this far away from the basket, then I can estimate somewhere around here would be the answer for how many baskets they're making. Or even if I pick this point here where there is no dot, I know that the number of baskets certainly isn't going to be way down here, and it's not going to be way up here. It's going to be somewhere in this area here. So we can definitely estimate. And finally, the third one, this is the house price versus the age of the house. So how many years old the house is versus how much the house is selling for. The graph shows the plotted points scattered. Yes, I agree with that. They're all over the place. As the age of the house increases, the price of the house is either large or small. Yes, so we've got houses that aren't very old, that don't cost very much money, like this one. And then we have houses that are pretty old, that don't cost a whole lot more. We have houses that are very new, that cost a lot of money, and we have houses that are very old, that cost a little bit more money. So, I agree with that. And the graph can't be used to estimate the price of the house if you know how old it is. I would agree with that. I don't know how much a house, say, that is this old, how much is it going to cost? It could be down here, it could be up here, we don't know. It's probably more like, it's not about how old the house is, it's about how well it's been taken care of. All right, fill in the blanks below with the appropriate words from the list: predictions, relationship, and trend. So this should be, this is kind of coming from the investigation that you did. A scatter plot is a graph that shows the relationship between two variables. The points on a scatter plot often show a pattern or trend. So if you take a look at these three graphs back here, the first one and the second one both are showing a trend. This one is showing an increasing trend. This one is showing a decreasing trend. This one is showing no trend whatsoever. So the points in the scatter plot often show a pattern or trend. And from the pattern or trend, you can make predictions. And that's the whole reason why we collect data and we want to make predictions. And what a great time to be considering data being collected through this whole COVID crisis. They're collecting data all the time, how old people are, what kind of underlying conditions they have, how severe they get COVID-19. And so all of this data gets collected so that we can make some kind of predictions. And so you heard about this whole idea of flattening the curve. Well, that was so we were trying to make it, the reason why we isolated was so that we could stop so many cases from happening all at once. You may have heard the term exponential growth. So that means if I have the infection and I give the infection to 5 other people, and then each of those 5 people give the infection to 5 more people, and then each of those 25 people give the infection to 5 more people. Now we started out with 1 person, and then we had a total of 6 people, me and the 5 people, and then they gave the infection to 25 more people. This is not linear growth. It doesn't grow in a straight line. It grows in a way that we call exponential growth. So instead of adding each time to get from one stage to the next, we would multiply by 5 each time. So that's called exponential growth. So we collect all this data and try to make predictions. So how terrible is this going to be on our healthcare system if we don't try to flatten this curve? And we were very successful in Canada at flattening the curve. We could have gotten it really, really bad. We could have been like Italy or like New York City, but we weren't. We caught it fairly early, and we isolated to flatten that curve so the problems in the healthcare system didn't happen. And that's why we collect data, so that we can make decisions that help us in society, that help us make decisions so that things can get better in the future, or to see how bad things are getting so that we can make changes. All right, so here we have some information about Julie and how tall she was at certain ages. And so it says label the axis, while the independent variable is age, so that goes on the horizontal axis, and the dependent variable is height. Her height depends on how old she is. It's not how old she is depends on her height. Her height didn't cause, or I don't really want to use the word causation, because you did find out that sometimes you look at the relationship between variables, but it's not that one is causing the other. And then on the vertical axis, we have height. And height is in centimeters and age is in years. Describe the trend in the data. Use words like increasing or decreasing, or use words like linear or nonlinear. Note, points don't have to be in a perfectly straight line to be considered linear. I'm going to jump back to these pictures again. Notice how I didn't connect the dots with a zigzaggy line. I just drew a line going up through the data, and I drew a line coming down through the data on the number of baskets, because in real life, many things are not perfectly linear. However, they show a bit of a linear trend. So even though points aren't on a perfectly straight line, there's still a linear trend as long as they're following a kind of straight line. So This data set, I would say, is increasing. And I say it's increasing in a linear fashion, as opposed to something like this. Let's suppose the points were looking more like this. It goes like this, and then there, and then like that. And suppose she grew like that. That would be a non-linear trend. Okay, so not all points have to show a linear trend. They also don't have to be on a perfect curve. So you get a curve with non-linear trends. But they definitely show that it's not linear. Again, we don't connect the dots with, I'm just going to erase this. We don't connect the dots with a perfect straight line. We draw a we don't connect the dots with a zigzaggy line to go from point to point. This is not a connect the dots situation. We want to draw a straight line, we will in a minute, that kind of follows the trend of the data. Okay, so describing the trend means what do the points appear to be doing? They're increasing. They're increasing in a relatively linear fashion. It's not perfect, but it's true. Okay, then describe the relationship. So what we want to do is describe how Julie's height changes as she ages. So clearly, as Julie gets older, she gets taller. Oops. Okay, that's pretty clear. So when you're describing the relationship, you want to use the variables that you're comparing or relating. So what is happening to height, which is the dependent variable, as age increases? So like back here, this is all about the second question in each of them. So as the length of the tibia increases, the length of the leg increases. As the distance from the net increases, the number of baskets made decreases. So as Julie gets older, she gets taller consistently. Okay, the independent variable is located on the x-axis. I already said that. This variable does not depend on the other variable. The dependent variable is located on the y-axis. This variable depends on the other variable. In this case, the independent variable is age, and the dependent variable is height. Okay, now the line of best fit. So you looked at some examples in the online activity, and so we're going to do one now. The line must follow the trend of the data. The line should go or pass through as many points as possible. There should be the same number of points above and below your line of best fit, as close as you can possibly get. And the line should pass through points all along the line, not just at the ends. And sometimes, to be honest, it doesn't pass through any of the points. Sometimes the line goes so through the center that it doesn't pass through any points at all. And that can happen. So sometimes doesn't pass through any. The point of this rule is that you don't want to simply pick the first point, pick the last point, and then draw a line between those 2 points. That's not how a line of best fit is drawn. Okay? We don't want to do that at all. And I'm going to cut that because I don't want it there. All right, so the line should go through what's called the mean point, which is the point made up of the average of the independent values and the average of the dependent values. So if you take a look here, I have an extra column, and that is for the mean point. And I'm missing my calculator. Hold on. Okay, so if you recall, the mean is the same thing as the average. So you want to add up all the numbers, hit equals, and then divide by how many numbers there are. So I'm doing 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, hit equals, and then divide that by 8, and I get 4.5. So the average age is 4.5 years old. Now, for her average height, 70 plus 82 plus 93 plus 98 plus 106 plus 118 plus 127 plus 135. Hit equals, then divide by 8, and I get about, rounded is about 104. It's 103.625. So now what I want to do is I want to plot that point. So 4.5 and 104 is about right here. And actually, I want to do that one in red because it's not part of the data set. So I want to make sure it stands out as not being part of the data set. All right, so that's number 5. The line should go through the mean point, which is the point made up of the average of the independent values and the average of the dependent values. Okay, now we're going to draw a line. It's going to follow the trend. It's going to go through as many points as it can, and that might be no points, except it will go through the red point. So I'm just going to draw a line here. Just a random line. Okay, that might be a good one. Your line might not be exactly the same as my line, and that's okay. It doesn't have to be exactly because we're only human, but what it can't do, it can't be down here. It can't be up here. It can't go through that point but not follow the trend of the data. It's got to follow the trend of the data, and it's good to get a ruler out. I wish I actually had a ruler, and I was doing this with a ruler right now. I'm going to draw it about like that. Notice it doesn't necessarily go through 0, 0. In fact, this one doesn't go through 0, 0 at all. But I have 1, 2, 3 points above the line, 1, 2, 3, 4, 5 points below the line right now. That's about the same number above as below. I might actually, and I want to extend it to make sure it goes to at least the y-axis. So I'm going to maybe do this. And I'm going to play with it a bit there. I kind of like that one right there. Okay? So that's done. Oops. All right, so there's a line. It follows the trend. It actually is going through a couple of points in my table of values. And I'm going to use that fact when I try to find the equation. So, next step, to find the equation, pick 2 points that are on the line that are not necessarily in the data set. They have to be sitting on the line. And sometimes you want to pick you might pick your 2 points on your own. So even though, let's say this point right here, see that point right there? That's not the same point as, so on 2, it's 82, but I'm actually picking 280 because 280 is actually on my line. This point here is also actually on my line. That's the point 6 and 118. I also know that my mean point is on this line, so that's 4.5 and 104. You want to pick friendly points. So friendly points are points that you either know exactly what the coordinates are, so they actually come out of your data set, like the 6 and the 118. 170 is another very friendly point. But a point like, say, oh, I don't know, say this one right here. That's not exactly, well, actually that's the 6th one. Okay, this point right here, just above the one that's in the data set. So at 8, in the data set is the point 8 and 135. So I'm talking about this area here, 8 and 135. So the actual point that's on the line would probably be more like 8 and 136. So I wouldn't use 8 and 135. That one's not being used. 2 and 82 are not being used. 3 and 93 not being used because it doesn't sit on the line. You need 2 points that are exactly on the line. So I want one of them to be my mean point because I know that one is on the line, and then I'm going to pick any other point. So the point that I'm going to pick is actually, let's say, this point, 2 and 80. Notice I'm not picking 2 and 82 because 2 and 82 is not on my line. It's in my data set, but not on my line. So the 2 points I'm going to pick are 280, and then I'm going to pick 4.5 and 104. And what I want to do is use the strategies from Unit 5 to find the equation of this line. So first thing I need to do is find the slope. So the slope, remember, is delta y over delta x. So you do the differences of your y's. So 104 minus 80. Remember, this is y or x1, x2. Oh, no. Forget that I just said that. Let's do that again. This is x1, y1, and this is x2, y2. So I'm doing y2 minus y1 over x2, which is 4.5, minus x1, which is 2. 104 minus 80 is 24. 4.5 minus 2 is 2.5. And when I divide those two numbers, so 24 divided by 2.5, that equals about 9.6. Now the units on my vertical axis are centimeters, and then the units on my horizontal axis are years. So that means that she is growing at an average rate of 9.6 centimeters per year. Take the S out of there. Okay, so now for the equation of the line, this is where we're going to use y equals mx minus x1 plus y1. So y equals 9.6 x minus 2 plus 80. So y, now you want to multiply this out. This 9.6 does not get multiplied by the 80. The 9.6 is next to the bracket. It's not near the 80. So 9.6x minus 19.2 plus 80. So y equals 9.6x plus 60.8. And if I look at the graph, remember this last number here, this one here, that one should be the y-intercept. And if I look at my graph, it does look like it's crossing the y-axis slightly above 60. So I'm going to say 60.8 is about perfect, okay? So you need 2 points that lie on the line, and don't cheat. Don't pretend. Don't draw your line really thick. This should be done with a sharp pencil and a ruler. If it's not, I'll give you 0 on it. sharp pencil and a ruler, and then this friendly word here was friendly points. Pick points that are easy to read on the graph. Either they're right on a corner of the grid, or they're a point that is actually from the data set, but they have to be on the line. On the line. I can't stress that enough. I see kids cheating all the time, saying, oh, well, this point, it's so close and I already know what the coordinates are, so I'm going to use it. No, 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 no. You have to use points on the line, because if you don't, let's say I have a line. There's a line. I have this point that's on the line and this point that's almost on the line, but it's not quite. But I use it anyway. Well, then I'm not trying to find the line of best fit for the line that I've drawn. What I'm actually finding is the equation of this line here, which isn't the same line. It's there. It's not the same line. It's a different line. And if I want to do any kind of predictions of what's going to happen, I'm going to over predict, because my answers should be on this line, but they won't. They'll be on this line. Or if I'm coming this way, I'm going to under predict. So you need to pick 2 points that are actually on the line. Again, they don't have to be in the data set. Okay. Now it says, now let's learn how to find the actual line of best fit using Desmos. And what I'm going to do is I'm going to stop this video and I'm going to start another one with Desmos open.